Hello everyone, this is Anju and this is a presentation about implementation of Dijkstra's shortest path algorithm using the Fibonacci heap. Uh, this is presented by all of the group members Anju, Rishabh, Bhavna, Sadikshita and Hamad. So let's go into this presentation of what is included in the following slides. So there is an introduction about why are we using this particular Fibonacci heap for implementing the Dijkstra's algorithm, and followed by overview of the Dijkstra's algorithm, the limitations of using the traditional data structures instead of the Fibonacci heap, and an introduction to the Fibonacci heap, like why are we preferring the Fibonacci heap over the traditional data structures, and implementation of the Dijkstra's algorithm for the Fibonacci heap, where we see the code and what it includes, and also the time complexity analysis of this whole algorithm, advantages and disadvantages of using the Fibonacci heap for this particular algorithm, followed by conclusion and the future directions. Here comes of why we are using Fibonacci heap particularly for implementing this Dijkstra's algorithm, and why are we using what is the use of this Dijkstra's algorithm for what is the use of this Dijkstra's algorithm which implements the Fibonacci heap. The shortest path problem is a task of finding the shortest route between 2 points in a graph where the distance between the vertices is defined by a certain metric, such as distance or cost. This problem has many practical applications in areas such as transportation, logistics, and computer networks. Like, for example, when you use a navigation app to get driving directions, it's finding the shortest path between your current location and your destination. Similarly, when a package is shipped from one location to another, the shipping company needs to find the most efficient route to deliver the package as quickly and cost effectively as possible. In computer networks, routers use shortest path algorithms to determine the best path for packets to travel from one network node to another. Finding the shortest path is essential, hence, for optimizing resource allocation, minimizing costs, and maximizing efficiencies in many real world scenarios. That's why it's important a problem to solve. And here comes the Dijkstra's algorithm using the Fibonacci heap, and followed by the overview of Dijkstra's algorithm. It's a famous algorithm for finding the shortest path between the nodes in the weighted graph. The algorithm works by starting at the starting node and visiting each of its neighboring nodes. It then calculates the distance to each neighboring node from the starting node and marks it as a visited. It repeats this process for each of the unvisited neighboring nodes until it reaches the destination node. Dijkstra's algorithm is guaranteed to find the shortest path between the starting node and the destination node as long as there is no negative weights in the graph. If at all there are any negative weights, a variant of the algorithm called Bellman-Ford algorithm can be used. Why particularly the Fibonacci heap and over the traditional data structures is what we are going to learn now. Like, traditional data structures such as arrays and linked lists have certain limitations when it comes to implementing Dijkstra's algorithm for finding the shortest path. Like, for example, using an array to store the distance from the source node to each of the other nodes in the graph would require a lot of memory, especially for large graphs. Additionally, updating the distances in the array after each iteration of the algorithm would be a time consuming process. Similarly, using a linked list to keep track of the nodes that have not yet been visited would require searching through the entire list to find the node with the minimum distance. This could become very slow for large graphs. So, to overcome these limitations, specialized data structures such as priority queues or the Fibonacci heaps are used in implementing Dijkstra's algorithm. These data structures allow for efficient storage and retrieval of elements based on their priority. In this case, the distance from the source node. As we have seen why Fibonacci heap is used over the traditional data structures, we will now see what exactly is this Fibonacci heap. It's a collection of the trees that satisfies the minimum heap property. Each node in the heap contains a key and the degree value. The degree value of the node is the number of children it has. The minimum heap property ensures that the key of the node is less than or equal to the key of its children. The main advantage of the Fibonacci heap over the traditional heap data structures is its ability to perform certain operations in constant amortized time. This makes it particularly useful in algorithms that require insertion and deletion of elements from the heap. In the construct of Dijkstra's algorithm, Fibonacci heap is used to keep the track of the unexplored nodes and their distances from the source node. The ability to efficiently update the distances of the nodes in the heap is what makes Fibonacci heap particularly useful in this algorithm. The core of the Dijkstra's algorithm, that is to implement the Dijkstra's algorithm with Fibonacci heap, as you can see, it implements the using Fibonacci heap. Uh, uh, what you have to do is you need to first represent the graph as an adjacency list or matrix. Then you would initialize the distance of the starting node to 0 and the distance of all other nodes to infinity, or you would also initialize the Fibonacci heap at the starting. Uh, but coming to this code uses Dijkstra's algorithm to find the shortest path between nodes in the graph using the Fibonacci heap data structure to efficiently find the node with the smallest distance from the starting node. The function takes two arguments, graph and a start node. The function takes two arguments, uh, that is the distance dictionary stores the shortest distance from the start node to each node in the graph, and the visited set keeps track of the nodes that have been visited during the algorithm. The while loop continues until all nodes have been visited, and the for loop iterates over all the adjacent nodes and waits of the current node to update the distance to the adjacent node. The function returns at the end the distance dictionary. It is what that explains the code that has previously been discussed, as it explains about the while loop, the for loop, and what has been implemented exactly in the Dijkstra's algorithm using the Fibonacci heap. The Dijkstra's algorithm, as said, uses the Fibonacci heap, and this explains what is included in the Fibonacci heap code. The Fibonacci heap is implemented with two classes, Fibonacci heap and Fibonacci heap node. The Fibonacci heap class, it has the following methods, which is described in the next slide. It it has this initialize. It is having an initialized and empty Fibonacci heap, and is empty method returns the true if the heap is empty, or else it returns false. And add node self key value adds a new node with the specified key and value to the heap and returns the new node. And it is having a remove minimum node self removes and returns the node with the minimum key from the heap. Decrease key decreases the key of the specified node to the new key value if the new key is greater than the current key, and a value error is also raised here. Deletes the specified code from the heap, that is what the delete node method does. There is a merge method, merges the current heap with another Fibonacci heap. And also there is a find node method, returns the node with the specified key value or none if the key is not found. And here comes the Fibonacci heap node class, represents a node in the Fibonacci heap, and it has the following attributes as mentioned: key, value, parent, child, left, right, degree, and marked. These all represent the different attributes in this class. It does these different functions, like the key is the key value of the node, the value is associated with the node, the parent node of the current node, the child node of the current node, left, the node to the left on the current node, and right, it is the node to the right of the current node. Degree, the degree of the node, that is the number of the child nodes. Marked, a boolean flag that is used to mark nodes during cascading cuts. The Fibonacci heap node class has the following methods. It also has an initialize method that initializes a new Fibonacci heap node with a specified key and value. It also had add child method, adds a specified node as a child of the current node. Remove child. This method removes the specified node from the child of the current node. Coming to the time complexity of the Dijkstra's algorithm using Fibonacci heap. Dijkstra's algorithm using a Fibonacci heap has a time complexity of big O notation of E plus V log B, where E is the number of edges and V is the number of vertices in the graph. The Fibonacci heap data structures allow for faster updates of node priorities, reducing the time complexity of the algorithm. Overall, the algorithm is efficient for sparse graphs with many vertices and few edges. The pros and cons of using this algorithm. The advantages include the faster operations. Fibonacci heap has faster amortized time complexity for key operations like insertion, deletion, and decreased key. compared to traditional binary heap based implementations of priority queues, making it suitable for algorithms that rely heavily on these operations, such as Dijkstra's shortest path algorithm. Space efficiency. Fibonacci heap uses less memory compared to binary heap based priority queues due to its use of pointers and a tree structure, which can reduce the number of nodes needed to represent the same heap. The heap it also has an advantage of the flexible structure. The heap can be used for more than just priority queue operations, such as maintaining sets of disjoint elements or implementing graph algorithms. Fibonacci heap also has this disadvantages. The Dijkstra's algorithm implementing it also has this disadvantages like complex implementation. Fibonacci heap is more complex to implement compared to binary heap based priority queues, which can make it harder to debug and maintain. It also has a disadvantage of large constant factors. Although the amortized time complexity of Fibonacci heap operations is faster, the constant factors involved can be quite large, making it slow for small instances or in practice when the number of operations is not high enough to amortize the cost. It has poor cache locality. The tree structure of the Fibonacci heap can result in poor cache locality, making it less efficient for some architectures. In conclusion, Fibonacci heap is a powerful data structure that provides efficient operations for many graph algorithms, including Dijkstra's shortest path algorithm. Its main advantage is its ability to perform insertion and deletions in constant amortized time, which makes it particularly suitable for dynamic graphs. However, its main disadvantage is its large constant factor and higher memory usage compared to other data structures, which make it less suitable for small graphs or environments with limited memory resources. In terms of future directions, there is an ongoing research improving the practicality of Fibonacci heap and addressing its disadvantages. One direction is to investigate different memory allocation strategies to reduce its memory overhead. Another direction is to explore alternate data structures such as pairing heap or ranked pairing heap, which offer similar amortized time complexities for insertion and deletions with lower constant factors and memory usage. Finally, there is also ongoing research on combining Fibonacci heap with other structures to exploit their complementary strengths and achieve better performance. Overall, this presentation concludes with a key takeaway that implementation of Dijkstra's algorithm using Fibonacci heap is more better than using any other traditional data structures or any other shortest path algorithms. That it is better. Yeah. Thank you.